In 1847, James Prescott Joule published about 10 years worth of experimental results that changed our understanding of energy in a fundamental way. And that was the same year that our understanding of mechanical energy had been solidified with the theorem that related how much work is done to an object to the amount of kinetic energy it gains. So, in that year, really, one could argue energy as a part of science and a part of physics was really truly understood. And heat is part of that story as well. Previous to this, heat had been thought to be some other kind of thing, like a material, even, maybe a fluid, that flowed in the spaces between atoms. And this fluid was often referred to as caloric, which you can note that the word caloric is related to the modern day word calorie. And so, in that sense, still has its place in science. But the concept that that really comes from doesn't. We don't think there's some other kind of substance that explains how one object can heat up another object. And that was really fundamentally changed in 1847 with the experiments that I was talking about that James Prescott Joule had done. So in this topic, we're focused on heat, and when I say so, I say on the key concepts page that heat is a transfer of thermal energy. So in our language, we have to be a little bit careful distinguishing heat from thermal energy. I'd say this will be a continuous process probably for anyone because I still sometimes struggle to use the correct word at the correct time. Because if I say an object contains heat, that's an example. That makes sense if I say that, right? That object has a lot of heat, maybe because it's really hot, right? Like if I point at some lava and say that has a lot of heat, I think we'd all say that that seems reasonable. But the more correct thing to say would be that has a lot of thermal energy in it. But if I say I'm near it and I'm experiencing a lot of heat, that might be a better use of the word heat because heat really represents the transfer of thermal energy. It doesn't really represent the idea of an object containing a certain amount of thermal energy. Heat really, maybe better. I mean, it is kind of, you could say, is it a verb or a noun, right? And I think it can be both because you can say, well, we're going to heat this object, right? But you can also refer to the act of thermal energy transferring in as an object kind of thing as well. Okay, that might be enough English for me for one sitting. I just got to say, so I'm going to stop there. But again, the use of this word is subtle because we can't really claim that an object contains heat. It really properly contains thermal energy. And so, in that sense, when we say heat is a thermal energy, as I have done here on the key concept slide, maybe it's a little bit remiss to not have talked about, well, but what is thermal energy? And that's something that we're going to delve into in a little bit more detail further down into some of the topics we're going to get into. But for right now, if I state thermal energy equals randomized mechanical energy, at least to an extent, that answers the question. Or maybe it doesn't, because if you say, well, when do we see that, right? Well, thermal energy is also associated with an object being hot, right? Um, if an object has a lot of thermal energy, usually it means it has a high temperature. But on the other hand, that correspondence is not totally precise when we look at, in fact, the next topic for this lecture series is going to be specific heat. And that's what that's going to be about, is because it really depends on the object, what it's made of, how big it is. So one object could have a lot of thermal energy but still be at a low temperature if it's a really big object, let's say, or if it's made out of a material that can absorb a lot of thermal energy without necessarily getting to a very high temperature. Other objects get there more easily. So that's where things get complicated as well. But really, thermal energy represents the sum total of the energy that that object contains that is measured indirectly when we measure its temperature. So in that sense, temperature is a different thing, even though it is, in a certain way, it does measure it. Anyways, that's something we're going to explore in more detail in the future. When I say it's randomized mechanical energy, what that really means is a deeper understanding that has really developed over years in physics is that when an object is hot, it means that its microscopic constituents, in other words, the molecules, generally speaking, the molecules, you say molecules and atoms, maybe depending on what you're talking about, uh, are moving and therefore have randomized mechanical energy. So if it's a gas, as we've seen with the kinetic theory of gases, the higher temperature a gas is, the more it means the gas molecules are moving. Although how much, like how fast they're moving, also depends on the mass of the individual molecules, as we have seen. But in that sense, the amount of thermal energy contained by the gas is also related to that random motion of those molecules themselves. I put randomized mechanical energy, though, rather than randomized kinetic energy, because in solids, atoms can be oscillating, and they will have, in addition to kinetic energy, they can also have randomized elastic energy. So that's why I wrote this in a somewhat more broader sense with mechanical energy. Anyways, as we've said, though, heat is a transfer of thermal energy. So we're going to explore a little bit later that there are different ways that this can occur, but as a simple definition, this is what it is. If heat represents a transfer of thermal energy, that's kind of analogous to how work represents a transfer of mechanical energy. You do work, something through a force times displacement, you just transferred energy from one thing to another. And usually it's in mechanical forms, although there can be friction. So in that sense, work could create mechanical energy. It can also create thermal energy. Heat generally, most directly, I don't know if I want to say this is always true, but I think generally creates thermal energy. But there are examples, and we'll see this a little bit in the next chapter, where you can create thermal energy and then create maybe a mechanical form of energy out of that. So I hesitate to make a kind of blanket statement that winds up not really holding true all the time. But what I am trying to get across is the idea that heat really is maybe analogous to work, in the sense that heat and work are really the two ways that energy can be transferred between systems. So in that sense, we have a mechanical way of doing it through work, but we also have this thermal way of transferring energy through a heat kind of process. You could even say maybe a heating process. So getting back to the key concept slide, it makes sense then that if heat really is a transfer of energy, that the unit of heat should be the joule. And this might also explain why it is that the result that I started talking about from 1847 of James Prescott Joule, why that led to the unit of energy being named after him. As I mentioned, though, the calorie still persists to this day, and it's something that is out there, especially like, when we look at like food calories, for example. Turns out there are a number of different definitions of calories. They all come from the original idea of this caloric fluid. That is what people thought heat was before we came to understand it more deeply as an energy form. So one of the results that came out of James Prescott Joule's experiments is a relationship between how many joules of mechanical energy are in a calorie, or in this case, it's saying the number of, I think it is saying what I just said. The thermochemical calorie is equal to 4.184 joules. In other words, there's 4.184 joules in a thermochemical calorie. I said thermochemical here because it turns out if you Google this, you can find there are a number of different definitions of the calorie out there, and this is the one I'm adopting here, but you will find slightly different conversion factors for different calories. So if you look in different textbooks, you will sometimes see some different numbers for this.